Alright, so the start of momentum, my favorite topic, because it's so simple. We like to call it, in AP physics, we call it Pomentum, maybe with an arrow, because it's P. Does anyone know why it's P? Okay, so you have two masses like the carts M1, V1, and they can have signs, right? We'll do just linear momentum for starters. It's called, well, I like to call it Pomentum, and you're welcome to use other notation for after. I like just the prime for after, before and after. There's other types of momentum that don't have a letter P, like angular momentum, and so they'll have different names. So I like to call it Pomentum instead of just momentum. The letter P was Isaac Newton didn't really. It turned out that his laws of motion defined what momentum really was. He was explaining what momentum is, mass mv squared. And we'll get back to Newton's laws probably on the next slide. But he just called it progress. Like when they said you can't stop progress, they weren't making like an economic or political or technological statement or whatever. They're just literally a rhinoceros moving has a lot of progress. You can't stop it progressing towards you. No, that's what they meant. That's the word they used back in Newton's day. So it's P for progress, but we don't say that anymore. Uh, so the sum of the progress or momentum, m times v, before the collision has to equal the sum after. So you have a v1 prime. Same masses. We usually don't change mass unless we get into rocketry. That's pretty fun. Um, so and unless so in instantaneous collisions, momentum is absolutely conserved. You can kind of transfer it to the earth. You can have drag forces. You can have friction. You could over time you could get rid of it, but it just transfers to the earth. It's absolutely conserved. In fact relativistic momentum is permanently conserved in our universe forever. So if they ever ask you, is momentum conserved, you should default to yes. That's always a good guess. They might throw a weird situation where it's not conserved because of the way they defined a system, right? If I define the system as only these two blocks, these two carts, and they collide, momentum has to be conserved. If there's friction between the ground and then the system is the two carts plus the earth, in that system, momentum is conserved, but it doesn't always stay in the carts. Okay, so momentum is conserved, period, but if you have friction and you only define the carts, it could be not conserved. Does that make sense? I explained that a little bit backwards. Okay, alright. Okay, here is what Isaac Newton pointed out. Okay, if you actually have, we'll do final minus initial, and his calculus tricks were so good. This is the same mass with velocity 2 minus the same mass with velocity 1. You could just call that m delta v. And so the change of momentum over time, we could do t2 minus t1. Equals m change in velocity over change in time. Well, what's change in velocity over change in time, AP students? Acceleration. So mass times dv dt equals mass times acceleration. Yeah, we jumped over to calculus. What's mass times acceleration? Yeah, the net force. They're like, man, Isaac Newton, you're even more brilliant than you thought. Not really. His head couldn't get any bigger. But, hey, that whole trick with the net force, that's actually your exchange rate of momentum. That's why those action-reaction forces are so important. Yeah, you can't act on something unless it reacts on you, because you're literally exchanging momentum back and forth between those objects. It's the rate of change in momentum. That means you could have something called impulse. That's literally the change of momentum, but it could be like the instantaneous change. And it's also equal to the force, so that's what we do. If the force is some weird function of time, let's make the force a function of time, function notation. We could take the antiderivative of the force and get the change of momentum, which is what we have to do if there's collisions, if there's in rocketry you have to do this. Rockets are especially complicated because the mass of the rocket, you're ejecting fuel, so your mass actually is decreasing. And the change of the derivative of momentum with respect to time, it will have a term if your velocity is changing at all, but in rocketry it will have a term because the mass is changing. If you're ejecting fuel out the rocket, then your mass is actually decreasing, and you still get a boost from the force of ejecting your own fuel, and so on. Okay, so great. Change of momentum over change in time is actually mass times acceleration equals net force. Momentum is absolutely conserved unless they pull a system trick, a frame of reference trick. Oh man, yeah. We'll spend a few days on this. It's pretty fun. Explore the options. Any questions so far? Oh, still writing. Excellent. Okay. We're up to 6 minutes on video. Tell you what, while you're writing, I'm going to switch videos because I'm sure this next part will take 15 minutes.